But I guess, Super, you can get started now.
Okay, thank you, Joel, for this invitation. I'm very happy to be here at this mathematical physics webinar. And in fact, the things I'll talk about involve a lot of quantum statistical mechanics, but I'll and also connections to experiments. And I will try to give a overall picture. And the link to this article is in the chat if you would like to know more. It's a recent article I just put on the website. I should also mention a more comprehensive review article written with my former student Main Christos, postdoc Pietro Bonetti, student Alexander Nikolenko, and former student Avishkar Patel. And I probably won't get to this, but there's also a collaboration with lattice gauge theorists in India, which plays an important role in some of the things I'm talking about. All right, so to get started, this is all of the problems I'm looking at in this talk were motivated by the cuprate high temperature superconductors, yttrium barium copper oxide being one of the most prominent of them. Here's a little picture of what they look like, discovered in 86. And, they're still the best superconductors you can have. And in fact, one of their more exciting possible applications is used as magnets in fusion machines. So you can make much stronger magnetic fields over a much more compact space. And there are several companies around the world which are in fact using YBCO. These are wires of YBCO. That it takes a lot of high technology to make these wires. Well, let's see if this works out. But this is something that's attracting a lot of both government and private funding these days. All right, so the material is rather complicated, but for almost everything I'll talk about, you just need to focus on the copper atoms, which form a beautiful square lattice. And even more simply, there's only one orbital on each copper that's active. So you just need to think about a simple model on the square lattice where you can have 0, 1, or 2 electrons on each site. Now there's a parent insulator at a certain density of oxygen where you have exactly 1 electron per site. And these electrons have an antiferromagnetic exchange interactions. So J is positive and quite large. I mean, that's what's special about the cuprates. J is, 1600 Kelvin or even higher. And these are spinor halves. So they're really quantum spinor halves. And the quantum nature of the spinor half is absolutely crucial. Now, if these spins were classical, they would form this two sublattice antiferromagnetic arrangement. But it turns out that for spinor half is quite classical. It also forms the same arrangement, although the moment at 0 temperature is not the full polarization. There are quantum fluctuations about this state. So what we are interested in is what happens when you remove a few of these spins, and the density of the spins you're removing from the copper sites is P. So I'm going to call this P, will refer to that. It'll play an important role in everything I'm talking about. So you remove a density P of these holes. And that's when at some temperatures for certain values of P, you get this remarkable phenomenon of high temperature superconductivity. So in 1987 and then in 1988 with Bhaskaran, Phil Anderson made a suggestion, which if it hasn't had a big impact on cuprate physics, it certainly had a huge impact on just the theory of quantum phases in quantum information theory, quantum computing, and so on. So it was a theoretical idea which was very ill-formed at that time, but today we have a much more sophisticated understanding of the state that Phil Anderson, which he called the resonating valence bond, proposed. And my talk is really about applying that much more sophisticated understanding today back to the original problem from which the idea came. So what he proposed was that the spins, instead of being anti-parallel as in this arrangement, if the spins are anti-parallel, that doesn't optimize the energy of the quantum energy. That is not the lowest possible energy for two spins. The lowest possible energy is obtained when they form a spin singlet, which is a coherent superposition of these two states. So you can certainly form spin singlets by pairing the electrons in some configuration. And so each of these dimers here then is perfectly optimized, but then the remaining dimers are not. And to fix that, he proposed the resonating valence bond state, which is kind of a generalization of states that appear in chemistry for benzene and also discussed by Linus Pauling, but here applied to an infinite lattice. So you've got many possible dimer coverings of the square lattice, each of which forms one component of this wave function, which is the coherent superposition of an exponentially large number of dimer configurations. So, in a system of size n, the number of dimer coverings is e to the n. It's exponentially large. So it's a huge number of configurations. And the proposal was that this is a new type of quantum ground state in which you have a coherent superposition of such a large number of possible configurations. Now, the trouble, and so, in fact, the wave function then involves all of these different states. Now, the trouble is, even if this happened, it's not so easy to tell. If you were to look at the system, and today you can actually look at individual spins in cold atom experiments, you would only see one configuration. It would collapse onto the one particular configuration. You never know just from that type of observation, but whether it was a part of a coherent superposition or just some random thermal fluctuation. Okay, so that was the idea back then in '87. But today we have a very sophisticated theory of such states of matter. And there's very powerful ways of characterizing them and different ways of measuring the long-range entanglement that they have. So I'm not going to go into that, but I think let me just summarize all this theory by what I think is the most basic property, novel property of such a state. And the novel property is this: it's really fractionalization, that the excitations of the states are particle-like, at least in 2 dimensions, but they cannot be created by local operators. So for example, if you take this particular state and you hit this bond and break the 2 spins, that's not actually in this kind of resonating valence bond state, the right elementary excitations. What happens is that one of these runs off to infinity, and then you're left with this object, which you cannot be created by a single operator, any local operator, which is in fact the true excitation that describes the dynamics. And this object, as it moves around, carries spin a half and no charge. So that's the fractionalization. So, if you open up any condensed matter textbook before the 1980s or even the 1990s, Landau, Lifshitz, or Mahon, or anything, there's nothing in there, no analysis you could make that would ever give you such an object with spin a half and charge E, which is able to move around in a system that doesn't break any symmetry. This can happen in 2 and higher dimensions, but actually it can't happen in 1D. In 1D, you can get fractionalized excitations, but they involve some domain walls and broken symmetry. Here you can get them in 2D as just fractionalized excitation. So that's the essence of the idea that these fractionalized states are somehow important proposal really at that time to the physics of the cuprates. And as I've said, the biggest impact of this idea has been not so much here, but in quantum error correction and theories of topological phases and so on. Okay, but let's get back to the cuprates then. So here's a phase diagram as a function of P and temperature. There's a lot going on, but let me begin with the region we understand extremely well, which is the higher P region, where, for example, if you measure the density of holes by the density of charge carriers by the Hall coefficient, you come up with a density of holes of 1 plus P. Now, this might seem surprising because I told you the density of holes is P. Well, the point is that this is P with respect to the antiferromagnet. And if you were a conventional card-carrying solid-state physics, you measure in the semiconductors, for example, you measure the density of carriers with respect to a fill band or an empty band. The antiferromagnet is not a fill band, it's a half fill band. But if you were to fill it, then the number of holes here is in fact 1 plus p. But alternatively, you could take an empty band. With respect to the empty band, the number of electrons, as you can see from the picture, is 1 minus p. So why is the Hall coefficient 1 plus p rather than 1 minus p, but the opposite sign? That really has to do with basic solid-state physics, has to do with the shape of the Fermi surface. So this is the Fermi surface as measured in photo emission. And in fact, these are the occupied states here, and these are the empty states here. And the occupied states form a simple closed circular Fermi surface centered at the point pi pi. And that's why there are holes. The Hall coefficient is positive. It's because of some microscopic physics and the shape of the Fermi surface. And that's why you get 1 plus p electrons, 1 plus p's. So that's beautiful. Exactly what you would expect from conventional band theory. And even more, there's a very deep theorem, which was discovered already by Luttinger in 1960, which said that independent of the strength of the interactions, and as long as you're smoothly connected to the free electron state, which is required for his proof, then the statement was that the area enclosed by the Fermi surface, this area, if you count electrons, or this area, if you count holes, is the same as that of free fermions. And that's also very beautifully verified in the experiment, and also as part of density functional theory and many other approaches. So this theorem, which was discovered in 1960, got a modern outlook by Oshikawa. And I won't go through Oshikawa's theorem other than mentioning that his proof is a lot easier to read. It's just 2 pages of beautiful argument, which is actually more powerful, as you'll see, than Luttinger's argument, because it's non-perturbative. And he just gave the same result, but he associated with what we today would call an anomaly. There's an anomaly in the system which you can compute exactly, and then you assume the only low energy excitations are quasi-particles near the Fermi surface, and then if you look at how those quasi-particles satisfy the anomaly, you get Luttinger's result. All right, so that's the part where everything looks great. You've got a Fermi liquid, which if you cool it down, you get a superconductor. But this is not the most interesting part of the phase diagram, because the superconductivity is at relatively low temperatures. So now let's go to the lower doping region, which is what I'm going to focus on in this talk. So this is called the pseudo gap. It's again a metallic state. And here you indeed see the Hall coefficient that you might naively have expected of P, of holes of density P. Now, this is perfectly easy to understand if you were in the antiferromagnet. But you see this Hall coefficient of P at much higher values of doping, where there is no order. So this is the key mystery that I'm going to discuss in my talk. How do you understand, and many others have talked about it over the years, how do you understand this carrier density P in a region with no order? If you look at photo emission, you get some rather complicated arcs, and I probably won't have time to go into the theory of these arcs. But let's just focus on how do you get carrier density P for now. Well, so there's been a huge amount of work on this, and I would say the majority of theories work with fluctuating orders of some type. Fluctuating antiferromagnetism, thermal fluctuations of various broken symmetries lead to some thermally fluctuating state, which could, under certain conditions, have carrier density P. All right, well, that's not the point of view I'm going to take directly. I mean, there's so much to be said for these theories. They do explain many experimental observations. But as you'll see, they have serious difficulties with some more recent observations, which I will talk about. So we're going to explain this by a new quantum state that we proposed in 2002, 2003, which we call a fractionalized Fermi liquid. So in fact, we're going to say that this state is also really a zero temperature state, which has been raised to finite temperature. So the point of reference is a quantum metallic state, which has no broken symmetry. But nevertheless, that state has a Fermi surface which actually violates the Luttinger constraint. And that's allowed, and I'll show you how. But the more powerful Oshikawa anomaly must be obeyed because it's really exact, and it does obey the Oshikawa form of the result. So that's really going to be the main topic of my talk. And this state also has a possibility for all these broken symmetries, but they're described not by the usual Landau approach of autoparameters, but really in terms of fractionalized autoparameters, which we think of as a Higgs field. So there's a Higgs field B, which carries an emergent gate charge. In fact, it turns out to be SE2, we claim. And various composites of this Higgs field play the role of the autoparameter. Okay, but I won't really have time to go into that, I think. All right, so let me construct this state and first of all define what this is and how do you at least write down a toy wave function for it. What is this fractionalized Fermi liquid and how do you violate the Luttinger argument? So just to remind you, the Luttinger argument is that if you have assuming spin rotation symmetry and everything I'm talking about, carriers of density rho, which is 1 plus p, then the area enclosed by the Fermi surface is rho over 2. This is the point pi pi in the cuprates. The 2 is for spin degeneracy. And this is measured in units where the area of the square is 1. So all the factors of pi and peculiar units disappear. You just measure in units of the Brillouin zone, and then it's very easy. It's just the density divided by 2 for spin. All right. So the fractionalized Fermi liquid, as I've already said, is a state, again, breaks no symmetries, but the area is rho minus 1, which is the same as p. And the factor of 2 for spin will give you, coming from the spin degeneracy. So if there happen to be 4 different pockets, the area of each pocket would be p over 8. Okay, so how is this even possible? Well, I'm going to show you how it's possible, but it's a direct consequence of the existence of a background spin liquid. So, as I mentioned earlier, even if there was a spin liquid somewhere, it's very hard to tell that there is a spin liquid. And what we've been arguing for a while is that, in fact, one of the best ways to see the quantum entanglement of a spin liquid is to measure the size of the Fermi surface. And deviations from the Luttinger result are only possible by the presence of a spin liquid. So detecting this Fermi surface is essentially a direct evidence for the presence of a spin liquid. And okay, so that's what I'm going to talk about. All right, so let me now show you how, what are the candidates for the pseudo gap in some very simple terms, and what would be their Fermi surfaces, and so on. So of course, let's start with the antiferromagnet. This has a broken symmetry, and then this is your Brillouin zone, the blue dashed line. And then you put in a density p holes while preserving the symmetry, while having the broken antiferromagnetic symmetry. This has in fact been studied, and experimentally you see exactly what you expect theoretically. So because of the broken symmetry, we don't need to worry about the background. You can really think of it as density p holes. And these, in various computations, form 4 pockets. But actually, the point is that the Brillouin zone is halved. So there's actually only 2 pockets. This pocket is the same as that pocket. This pocket is the same as that pocket. So there's 2 pockets, but there's a spin degeneracy of 2, and the area then should be p over 4. And this is exactly what's seen in experiments. All right, so that's the conventional state, no problem. There's a broken symmetry, exactly what you expect from the conventional theory and from the textbooks.
Subir, can I ask you a simple question? Yeah, the question is,
please go ahead.
Does it matter if you create all the holes near the edge of the system?
I'm just talking about what's happening in the bulk and assuming a uniform density. Yeah. Okay.
Thank you.
Yeah, I'm not talking about, right. Yeah, I'm talking about infinite systems. All right. Okay, so then another state, which is something that a huge amount of work was carried out on, is as the most natural generalization of Anderson's RBB state, where you just you form this resonating valence bonds, and then you just remove density P of electrons. Now, what is the state? Well, there's still a resonating valence bond. There's no broken symmetry. And you can see when then this vacancy moves around, it's carrying charge, but no spin. So this is another anion. It's a more exotic anion. It's spinless, but carries charge. Okay, now, if you want to get a metal, this better be a fermion. I mean, depending on the theory, it can be a fermion or a boson, but if it's a fermion, it'll form a Fermi surface. And to that exotic fermion, we can now actually apply the Yoshikawa anomaly. And the background spin liquid, as you can see, eats away exactly 1 electron per side. So really, the density of these holons is exactly P. So the area enclosed by the Fermi surface, after allowing for spin degeneracy, should be P. Now, you do get 4 pockets in many calculations, but these are spinless, so there's no factor of 2 for spin. And so the area is, again, P over 4. So the antiferromagnet and the holon metal have the same area, but these are for very different reasons. Here, the quasi-particles don't carry spin. And this means that, in fact, if you had many square lattice layers, these holons cannot tunnel from one layer to the next. They're really trapped within each layer. Anions are really a feature of the ground of the state that they're in. More technically, they carry an emergent gauge charge, and there's no gauge invariant operator that will take one holon from one layer to the other layer. So that will be important for the experiment I'm going to talk about. Finally, so that's not the right state. So the right state is this FL star, and how do you get that? Well, imagine the following thought experiment. Suppose I take the holon metal and I break a singlet and I get 2 spin-on. This is going to cost me the antiferromagnetic energy J. So the ground state, it seems I wouldn't want to do that. But now imagine that these spin-ons move around and each of them finds a holon. And now the holon and the spin-ons can resonate with each other. And this is going to gain you energy. The energy is the hopping matrix element of the electron, which is T. So in fact, you can form a bound state of the holon and the spin-on. This green is just this very simple electron hopping back and forth between nearest neighbor sites. And the energy gain is T. Now, T is generally factor 4 or 5 bigger than J. So you would think this should always happen. And that really was our claim. So these are holon spin-on bound states, are sometimes called magnetic polaron. And now you notice that this green object has exactly the quantum numbers of an electron. It has the spin of the spin-on and the charge of the holon, which gives you the same quantum number. So it is basically a renormalized electron. Now you might wonder, so it can move around, and it must be a fermion. But there are the background of resonating valence bonds. So if you looked at this in a colorblind way, you would say this is just the same old RVB state. But some of the bonds are actually fermions, and they carry spin and charge. And that's really the baby version of FL star. You might wonder, why did I fractionalize things and then put them back together to create the green dimer? Well, the simple reason is that you only put them back together for P of the electrons, not all of them, not 1 minus P. So now you have a gas of these green objects, which are fermions moving around. And by the same Yoshikawa type arguments, you would conclude that these should form a Fermi surface, and the area enclosed by the Fermi surface should be P, because that's the density of the green objects. Well, if you have 4 pockets, these are spinful. So there are 4 pockets, and the area should be P over 8, factor of 2 smaller, because of the spin degeneracy. So now we have a different result and of this more exotic FL star state. Anyway, so to summarize then, I've talked about 3 different states as candidates for the pseudo gap. This has antiferromagnetic order, and so that immediately rules it out. So the area of the pockets would be P over 4. But you could say, well, maybe there's just thermally fluctuating antiferromagnetism. Okay, so let's just keep that alive for now. This also has area P over 4, but these holons cannot tunnel from one layer to the next. And finally, this has area P over 8. Okay, so the point is, I presented these very cartoon-like pictures and got the basic result by staring at these pictures. It's really that simple. But the point is that these areas, they're sort of like topological invariants, similar to the Hall conductance of these states. These are exact results. And they would be valid for far more complicated states. And in fact, in the real world, the actual wave functions are far more complicated than these pictures. But the pictures are good enough to give you the areas. All right. So, and just to blow my own horn, there was a paper in 2007 where we explicitly pointed out this factor of 2 and how this FL star state should have an area of delta over 8, we called it then. Okay, so now I'm going to talk about some recent experiments. I'm going to focus on something that's only a year old, but there was a very important earlier similar experiment by Brad Ramshaw and Louis Taillefer, which is a bit more complicated to interpret, so I'm not going to talk about that. All right, so we're going to go back to the pseudogap, and I'm going to present one particular experiment to you. And this will be done, in fact, on this particular cuprate. And this is the point where I do have to worry about the dispersion in the third direction. So what's special about this cuprate is that the copper atoms are right on top of each other. So the dispersion of the electrons as they go from one layer to the next is very simple. In other materials, this is also very commonly studied. The copper here is not right on top of a copper. It's like an A-B-A stacking, and here it's A-A. And that turns out to be an important simplifying feature that enabled this recent experiment. All right, so this is the experiment, observation of the Yamaji effect. And I had never heard of the Yamaji effect when I saw this paper, but I explained to you about it. It's a very beautiful effect, which is a very powerful way of measuring the existence of a Fermi surface in regimes where you at somewhat higher temperatures. So they're going to sit in the pseudogap at a doping of 0.1 and a temperature of around 80 Kelvin in this material. And as I'll show you, they are able to explain the observation by assuming that the Fermi surface, there are 4 pockets, just like in all of the models I discussed. And what do? Well, they apply a magnetic field to the system, which makes an angle phi in plane and an angle theta with respect to this vertical direction. So they look at the resistance in this direction, along the C direction, as it's sometimes called, or the Z direction, as a function. As you vary the direction of the magnetic field, they're always measuring resistance in this direction, but you're varying the direction of the magnetic field over the entire sphere, theta and phi. And I'll show you the results in a minute. So if I take one of these pockets, that's an ellipse. So here's the X and Y principal axes of the ellipse. This is the dispersion. And along this direction, because this hopping is quite weak, you just get a simple cosine band. So this is what they assume for the dispersion. And this allows them to explain the experiments, as I'll show you. So what is the Yamaji angle or the Yamaji effect? So it turns out there's a very special angle called the Yamaji angle. At the very special angle, say this is it. Now, if your field is pointing in this direction, your electrons will execute an orbit in momentum space, which is orthogonal to the direction of the field. And the period of the orbit depends on the area enclosed by it. That's Ansaga's famous result. Oops, sorry. Okay, now it turns out that there is a very special angle, which Yamaji computed in '89, where this area to first order in T-perp is independent of where you draw the orbit. You could draw it here or draw it there. It's the same. It only happens at one angle. So this means that the orbits are independent of the z-axis. And that effectively means that you have no dispersion of the electrons in the z-axis. And so you have a flat band along this direction when the field is applied in this angle. And so the resistance should become very large because there's no dispersion in that direction. That's the crude, very simple argument due to Yamaji. And this has been seen in many other materials, non-cuprate materials before. But this is the first observation of this Yamaji effect at these higher temperatures. I should mention for the experts, there are, of course, at much lower temperatures. Why don't you just lower the temperature? Then people see the much more sophisticated form of quantum oscillations, Subnikov-de-Haas and de-Haas-Van Alphen. But the trouble is when you go to very low temperatures and high fields, there are other broken symmetries, which everyone agrees are there. And that complicates the interpretation of what the pseudogap state is. Anyway, so it's really you want to work at higher temperatures. And at higher temperatures, Yamaji is the poor man's de-Haas-Van Alphen, which in fact turns out to be just what you need. All right, so you take that dispersion and you put it into Boltzmann's equation, and you just compute the resistance along the c-axis. So these are their observations as a function of theta for different values of phi. These are the calculations, and you can see the fit is beautiful. So this is basically the observation, and these are the Yamaji peaks at the angles you expect them. So the observation of these are their words, is evidence for small Fermi subset pockets in the normal state. So this is really quite beautiful and evidence for pockets in the pseudogap state. All right, and what else do they say? Yeah, and not just pockets, but as you can see from the whole picture, these orbits are, going along the z direction. So this can only happen, these orbits only make sense if there's coherent tunneling in that direction. So it's really excellent evidence for whole pockets, which should be able to tunnel coherently from one layer to the next. So that pretty much rules out the whole on metal, the most popular state that people were thinking about who were taking a spin liquid point of view. And maybe it's an antiferromagnet. Well, it requires the antiferromagnetic order to be coherent from one layer to the next. And experimental evidence, at least at zero field, is that it isn't. But perhaps, putting a field here of, 70 Tesla changes that. And so, okay, that's still a possibility. And then they say the small size they actually figure out the size of the pockets, which you can from all these fits and the Yamaji angle. Estimated to occupy only 1% of the Brillouin zone is not expected given the absence of long-range broken symmetry. Well, okay, it was expected by us. The whole theory I'm talking about so far, in fact, did expect this. And then they say the size of the pocket is 1.3%. Well, I've told you that in FL star, it's P over 8 in these units, and that's 1.25. So exactly, very close to what we predicted. Whereas if it was this spin density wave or antiferromagnetic state, you would get P over 4, which is a factor of 2 larger and quite far. So I would say that, this is, I wouldn't say conclusive, but compelling evidence, and it's certainly the best evidence yet for the existence of these pockets, which have a size close to that of the spin liquid value of FL star. And so this is really, in some ways, if confirmed by more experiments and so on, really direct evidence, and certainly the best evidence yet, that there is actually a quantum spin liquid here in this FL star, in this pseudogap state. All right, so how am I doing on time? I have quite a bit of time. Okay, great. So that's really the punchline. I've given you the basic, very simple arguments and the experimental data that supports these arguments. And now I'm going to, this might be a good time for questions, if any, on what I've said so far. And now I'm going to take this idea of the pseudogap and try to apply it to everything else in the phase diagram.
Super.
Anyway, so if there's any, yes, please go ahead.
Slide, you had an equation involving some F. What was that F?
Oh, sorry. Excuse me. This?
Yeah.
Yeah, so this is
Yes.
just the Boltzmann equation. F is the distribution function of the holes. This is the classical Boltzmann equation with the Lorentz force.
How
So
is
if
it
you,
related to density matrix or what?
yeah, it's even simpler. It's just expectation value of C dagger C at momentum K and at time T. So this is just the usual, I mean, this F would be the Maxwell-Boltzmann distribution in equilibrium for a classical gas. For a Fermi gas, F would be in equilibrium would be F naught of E, which is this Fermi function. And now this is asking, how does the Fermi distribution get distorted when you apply an electric field and a magnetic field? So this is really the equation could have been written down by, I'm sure Lorentz wrote it down at some point. Boltzmann didn't know about the Lorentz force, I guess. But this is actually, they're just essentially the classical Boltzmann equation, as simple as can be. The only way quantum mechanics comes in, well, it comes in two ways. One is that the equilibrium value F0 is the Fermi distribution function. Boltzmann would have dropped the +1 here. And the dispersion, the dispersion E of K is not just K squared. It's also got this cosine in the third direction. So that's a quantum effect, the cosine in E of K. But so this cosine and the distribution, this +1 here is the only thing that's quantum mechanical about this. And that turns out to be enough to explain the data.
Yes, thank
so
you.
If you were doing a classical plasma, people in astrophysics were studying the sun, applying essentially these equations. But here I'm applying it to holes moving inside this metal.
I don't know, does it have any connection like with the Lindblad formalism for
No. Here, this is Lindblad. When you're connected to a heat bath. No, Lindblad puts in an external heat bath, which affects the dynamics. Boltzmann doesn't. Boltzmann is obeying just Newton's laws. It's a rewriting of Schrodinger's equation for the distribution function. There is no heat bath here.
no, but
as you yourself.
But something which makes something going to F naught. I mean, the right.
Oh yeah, there's a collision term. So the collision term, of course, has been simplified to this relaxation time approximation. But in reality, if you want to do a better job, you would put in impurities and put the collision of the impurities here. But that's that there's a lot of experience with that, and this is a pretty good approximation to the collision term. So the right hand side is the collision term.
Okay, thank you.
Yeah. So it's just as you've emphasized, this Boltzmann was he was just following Newton's laws, and with the collision term, his amazing equation gives you equilibration and increase of entropy. There is no heat bath or Lindblad and stuff going on here. Okay. Any other questions? Well, especially this is the key picture, the theory-wise that I showed you. So, oops, I'm going the wrong direction. Any questions on this picture? All right, so if you're all very happy with this, let me just go on and go to the next parts of my talk, where I'm going to very rapidly go through a lot of different things done over the years, building on this existence of FL star description of the pseudogap. All right, so first, what about the other metals? What about the rest of the normal state? So I've talked about the FL star, pseudogap being FL star, where I've got Hall coefficient of density P. And then at high doping, we know we get a conventional Fermi liquid. So for now, let me ignore everything at very low temperatures and ask, well, how do you go from one to the next? All right, so that's been a huge part of things we've worked on over several decades. So the idea then is that there are two phases, two different metals. So let's go to zero temperature, ignoring the other phases for now. So at zero temperature, you have this metal, which has carrier density P, made up of these green dimers, and which have density P, to just ordinary holes connected to free fermions where the carrier density is 1 plus p. And so there's no broken symmetry on either side, but just the existence of a Fermi surface which has different areas tells you right away that there must be a quantum phase transition between them. So there's a novel type of quantum phase transition which does not have any symmetry breaking on either side. So you can't use the usual Landau framework to talk about this transition. All right, so how do you talk about it? Well, it turns out that you can in the language of gauge theories. And this is something I won't talk about here, but it's in the references that I've given you. And basically, the bottom line is that the Higgs field, as is familiar to particle physicists, which carries an emergent gate charge, but doesn't break any symmetry under the right conditions, is exactly what's needed to drive this transition. So basically, you generalize Landau by going from bosons to Higgs bosons and adding a gauge field, and that gives you, it's a powerful enough language to talk about this transition involving change in the size of the Fermi surface. So in this case, it turns out that the Higgs condensed phase, in the way we formulate it in this paper, is the FL star, and the Higgs not condensed phase, which then confines for other reasons, is the Fermi liquid. All right, so in fact, I will pretty soon present what the theory roughly looks like. So now if you go to finite temperature, and if this is some kind of nearly continuous transition, you might expect some quantum critical region controlled by PC. And then an important question is does this describe the strange metal that's over here? Okay, so that's also a question. There's been an enormous amount of work, and many of the earlier papers, I did not get it right. And the reason is that, you may have lots of criticality and lots of scattering, but if this is happening from low energy processes, you will conserve the total momentum. So in fact, you need additional sources of momentum relaxation beyond just taking the continuum theory of the Higgs transition. And that's something, has been clear for a while, but also not clear in many other investigations. So you have to put in momentum relaxations. And so we've been thinking about it a lot recently, and you could imagine what's called Umklapp processes, which are allowed in perfect crystals, but it's hard to see how they could be really important at low temperatures. So you have to really think about the effects of disorder on this rather exotic Higgs transition in a metal. And it turns out that the most important type of disorder, which one could have anticipated a long time ago, is what's called the Harris disorder. It's the fact that some region of the sample are on the right of PC, the other region on the left of PC, and you really have to take that into account in writing the theory. So we have many papers on this in recent years, and I'll just kind of summarize what comes out of them. So here we were, in fact, in thinking about this Higgs transition, the work on the SYK model and its two-dimensional generalizations turns out to be very important. The SYK has connections to black holes, but on its own. But here you have to generalize it to a two-dimensional model, which I will very shortly show you. And this turns out to be the correct theory, we believe, for the strange metal, at least in the cuprates. All right, so let me give you a few equations, this being a mathematical physics seminar. So we begin by not the SYK model, but what people are now calling the Yukawa-Sachdev-Yekitev model, which was considered in different forms in various papers over the years. So what is this model? Well, it's a model with fermions, okay, but we take a very simple model where there's no dispersion whatsoever, with some label I, the n fermions, and then there's n oscillators. So this phi will eventually become the Higgs field, but here is just a bunch of oscillators with the same frequency, omega naught. And then finally, there's a Yukawa coupling, hence the word Yukawa, between the fermions and the boson. And this is a perfectly random coupling in all its indices, hence the word SYK. where you have random couplings between fermions. Here it's random coupling between fermions and bosons. All right, so this model turns out to be solvable in the large N limit, and really a lot is known about it today, partly due to all the duals to black holes, which I won't talk about here. But at n equals infinity, everything reduces to solving these type of equations, which are essentially the Eliashberg equations for electrons and phonons, but with no momentum space. And in this zero-dimensional form, these give you, in fact, critical solutions for all values of the coupling G. And in particular, you get this very important feature, which people now call Planckian relaxation, that the characteristic relaxation time or thermalization time, so the system will thermalize on its own. And the time it takes to thermalize is just h power over kt. In fact, it's the shortest possible time. And it's independent of the coupling G, which is quite remarkable. Nothing in Boltzmann equation ever anticipated that. Because there the thermalization time just depends on the strength of the collision term. Here, it's independent of the strength of the collision. The collision is so strong that they break down quasi-particles and give you this thermalization time. And of course, black holes are other objects that also share this feature of maximal chaos or fastest possible thermalization. Anyway, so that's the model. And where do you get a strange metal from this? Well, you really, this would be ridiculous to apply this to the cuprates directly. There's no dispersion in either the fermions or the bosons. So what do? Well, you add the dispersion. And so you put in a Fermi surface for the electrons, and then you put in some, actually the dispersion of the boson, not that important, but you can put it in if you want. There's a mass for the bosons, and then you put in the random Yukawa couplings and random potentials if you want, which are spatially random. So this model is not solvable at all, but you can solve it by various large N methods inspired by the zero-dimensional model, which is all I'm going to show you. Or you can study it by quantum Monte Carlo, which has been done especially by Avishkar Patel in great detail, but I won't have time to show you the results, which give very similar results, at least unless you go to very low temperatures, then there are various Griffiths effects you have to worry about. But I won't go into that. So anyway, you solve this model with a dispersion, and now it turns out it's not always critical. You have to actually tune this coupling S to see the phase transition, and near the phase transition, you do indeed get Planckian behavior. But very importantly, that Planckian behavior appears in transport. So this is, in fact, measurement of the transport relaxation time by optical conductivity. Here's the same data of the transport relaxation time as a function of frequency and temperature, which obeys this beautiful scaling form. And these are the results from the model, which give you, there's some breakdown in the theory here, which is due to the presence of certain logarithmic violations of scaling, and we don't fully understand why the theory looks better than the experiment looks better than the theory yet. Anyway, but it's really the simplest and, as far as I know, the only model which has all this Planckian behavior in transport, in the optical conductivity, in the resistance. It gives you also the famous linear T resistivity of the strange metal. All right, so that's what's happened in higher temperatures. Now, finally, let me kind of lower the temperature, where we have, of course, the elephant in the room, which is the D-wave superconductor. So this is the phase diagram I've talked about so far. The bulk of the talk was just arguing for experimental evidence for the existence of FL star. Now I've talked about, well, suppose there was some hypothetical quantum critical point between FL star and FL, and then in the presence of disorder, we claim that many aspects of this strange metal can be understood. But in reality, of course, when you lower the temperature, you don't have FL star down to zero temperature. Maybe someday in some material, people will see that I would, of course, be delighted. But in any material seen so far, there's always something else that happens. This FL star state, as you'll see, in a sense, confines. Okay, so you get what we do know in the most natural situation is you get a D-wave superconductor. And there's been a huge search over the years for any kind of phase transition without an autoparameter within the D-wave superconductor. Is there any sign of this PC once you get a D-wave superconductor? And the answer is no. I mean, there's no sign at all. So what the theory has to do now is to argue that if FL star and F undergo a transition to a D-wave superconductor, it should be the same state of matter. They should be smoothly connected. So that's a really important constraint on the theory that comes from observations. And so if you're going to develop any theory, it should obey this. Okay. All right, so what about the large Fermi surface? Well, if you start with the Fermi liquid and you have antiferromagnetic spin fluctuations, as was already talked about by Scalapino and others way back when, you will get D-wave superconductivity. And you can use essentially some generalization of Bardeen-Cooper-Schrieffer theory to describe not just transition, but also the state. All right, so, and the only difference then from the usual theory you might use, say, for helium-3 is that the temperatures are higher and it's antiferromagnetism rather than ferromagnetism that's relevant in helium-3. Okay, so that's fine. Maybe, and I believe that is a pretty good underlying theory for what's going on at high doping. But what about at low doping? Well, here, the FL star state is an exotic state with fractionalized anyons. The spin-ons are still present. So it has to be that these anyons and the emergent gauge field has to disappear when you go into the superconductor. So in fact, it has to be a confinement/Higgs transition. So here the point is that the transition itself, at least on the microscopic electronic scale, is very, very different. But the state you obtain at the longest distances is indistinguishable from the D-wave superconductor or BCS. It's the same state. It's the transition that's more exotic and it has to be really, because the normal state, the one underlying assumption the key underlying assumption of BCS theory is you start from a Landau Fermi liquid, and that doesn't exist. So the transition therefore has to be quite different, but that doesn't prevent you from getting the usual D-wave superconductor. Anyway, so this is a whole nother talk, which is covered in the review article I mentioned. And in fact, we get a theory here, which is an SU2 gauge theory. And the reason it's SU2 is because the spin-ons, we believe for many reasons, form this pi flux state of Affleck and Marston, which has an emergent SU2 gauge field. So, and you can think of these spin-ons as analogous to neutrons in theory of weak neutrinos in the theory of weak interaction. An electron, just the electrons. And there's a Higgs field that couples them all together, and that's this field B. And in fact, so the whole theory for the onset of superconductivity from the pseudogap is remarkably similar, minus the relativistic invariance of the Weinberg-Salam theory. Anyway, and what you find then is that the composites of this B give you all the superconductivity and even other parameters. Okay, so in the end, that's a bit disappointing, if you wish, that we're getting the same state anyway. And at the very longest distances, this is just an ordinary costless-Thouless transition. But there are detectable differences even in the superconducting state. And the most important are, in fact, in what's happening on the scale of the vortex. When you pull high magnetic field, you get a vortex lattice, and you can ask what's going on in the center of the vortex, which is, like a 10 angstroms wide at the most. But there's still a lot you can detect there. Also, there's obviously the difference in the photo emission spectrum up just above DC. Those are totally different, but the state itself there's no phase transition here. So this is something we took this is the work by this group. We took a theory of this Higgs boson, this SU2 gauge theory, but only did it in, I think you would call the Quenst approximation, where we don't have time-dependent fluctuations of the bosons, but only thermal fluctuations. And that's enough to give you a costless Thouless transition that you can see. I don't have the data for that. And so these are some of the vortices, which when they proliferate as you raise the temperature, seen in the phase of the pairing amplitude. So you can see the phase winding by 2 pi in the pairing amplitude. And so the phase winds by 2 pi in a charge 2e pair, even though the fundamental field we're working with is charge E. V carries charge E. And it has to do with the confining effects of the SU2 gauge field. And if you look at these points and you measure just the density, some kind of density operator, and you see that there are these checkerboard modulations at each vortex core. And this is a direct consequence of the underlying gauge structure and the Higgs structure of this theory. Here's a zoom in of it. There are period 4 modulations which appear for certain parameter regimes. And these are, to people in the field, would be, I think, very exciting because these have been long observed, especially in this beautiful experiment of Jenny Hoffman et al. Way back when in the cuprates in the underdoped side. So what's experimentally been seen is that you can see signs of this FL star to FL transition in the distinct vortex cores. At high doping, you get more conventional BCS phenomena and something called the Wang-McDonald peak, whereas at low doping, you see these structures, and this comes out very naturally without really playing with parameters too much in this transition from FL star to FL. Okay, so that's pretty much the end of my talk. So to then summarize, the main punchline of my talk was that there's very exciting new experimental evidence that the pseudo-gap state is really a quantum state to begin with, rather than some thermally fluctuating mess. And it's a quantum state you can think of as a mixture of resonating valence bonds and these hole-on spin-on bound states, which are the same quantum numbers as an electron. And these green dimers form, roughly speaking, a free Fermi gas. And there's evidence via measurements of the size of the Fermi pockets that, in fact, these have just the right quantum numbers for the Fermi surface that you see. So this exotic state should be then compared to this highly conventional state that every solid state physics course would start with, just the free Fermi gas, with some interactions which don't change the size of the Fermi surface. And then the second part of my talk has been about, thinking about what happens in the vicinity of this transition as a function of temperature and disorder. And I claim that, many things that are observed fall very naturally into this picture. So thank you.
Thank you very much. Let's unmute ourselves and give Suber a big hand for a very, very nice talk. Why don't you stop sharing the screen and have some questions or comments if there are any.
Subir, I have a question.
Yeah.
This is Tom Banks.
Hi, Tom.
Yeah. So in your description of the phase transition between FL and FL star,
right,
you had the Higgs field coupling linearly to ordinary electrons, but then you told us it was an SU2 gauge field.
There are a lot of indices I omitted for the sake of simplicity. Yes. So yes, that was just a simplification. You have to go into the review article to see the full structure. Yeah. So one of the fermions there is in fact carries a gauge charge, and the other is an electron. And yeah, so the whole thing has to be gauge invariant, of course. And there's also a gauge field which I omitted. But it turns out all of those features don't, in the end, make much of a difference. Yeah.
Okay. So if I read the review, I'll understand all of that.
Absolutely. Yeah, I think this review, which is in the chat, is something that you'll be able to read very quickly.
Thank you.
I hope. Yeah, everything's there. Nothing has been hidden. The whole thing is there in that review, at least for the theory of the FL star to FL also. Yeah.
Are there any other questions or comments?
Yes. Yes.
Yes, Very, go ahead.
Okay, so in this proof of the Hoshikawa of the Latinger theorem, there are assumptions. For instance, it is assumed that is a Latinger liquid, or so which are exactly the assumption of this?
Okay, so so let me present. That's a great question. I should have spent a bit more time on that. So there's an anomaly. So it's basically you put the system and you put it on a torus and you insert one flux quantum through the whole of the torus, and that gives you. And from that, you compute the change in momentum of the system from the induced electric field. That's just another way of saying there's an anomaly. And that turns out you can compute that exactly for any system. And the answer must be related to the density with certain factors. So that's an exact statement of the consequence of flux piercing, or an exact evaluation of the anomaly. So from the UV lattice Hamiltonian, you know the value of the anomaly for any system. It's not a problem. We know what it is. It's just basically the density, modulo integers. All right. So then you say, okay, I have certain state of matter, and you have to make certain assumptions of the infrared structure of that state. So if you assume that the only low energy excitations of your many body state are quasi-particles on the Fermi surface, that is the only low energy excitations you have. So that's an assumption. So then there's an if-then statement. If your only low energy excitations are quasi-particle on the Fermi surface, then the area enclosed by the Fermi surface must be the Luttinger value. I think that's the modern way to state the Luttinger theorem. All right, but the first clause could be violated. There could be some other low energy excitations. It could be a more complicated state. And so you have to compute. So in fact, the Hoshikawa anomaly could be satisfied by the sum of a Fermi surface anomaly, which in the FL star would be P, and another anomaly. So you have to find a state which has exactly the right anomaly. And in fact, spin liquids are states that do. So they also respond to flux in exactly the right way to give you the factor of 1. This is something you can actually see from the RBB wave function, and there's various much more sophisticated arguments today. So in fact, you're only allowed to have a certain class of spin liquids which have the right anomaly. And all the ones that were considered in the early days do have the right anomaly. There's various pi flux phases and other phases, and they all, just by the fact that the spin-ons are at half filling, the spin-on density is 1/2 in the background, and that's enough to give you the right anomaly. But it's quantized, so that's the other point. That spin liquid anomaly is quantized. The spin liquids only make sense at certain values of this anomaly. So that's why, because the Fermi surface, however, can take any size you want, but its deficit from the Luttinger value is quantized. So, it has to be P over 8. It can't be P plus X over 8 or something. You can only take away 1. And so that's the quantization that comes in. It's the quantization due to the spin liquid that quantizes then the Fermi surface size. And so it's really, I think, hopefully quite remarkable that this experiment is seeing, something very close to the quantized value that comes from the spin liquid.
Thank you.
Are there any other questions or comments?
I have a question. Subir, you jumped very quickly over a slide that had either a critical point or some very special parameter value that was something like 0.42. Could you go back to that slide and explain what that was about?
0.42, I don't remember that number.
Well, in one of your last slides, you I don't know if you displayed it or just passed by it very quickly, but there was some special point or parameter that you highlighted at the bottom of the slide, and I didn't catch what its meaning
Okay,
was.
I don't see any 0.42, but let me just show you the, okay.
Maybe it was the end of the antiferromagnet.
Oh,
Was it the place where the
perhaps
antiferromagnet
that's right. Yeah.
disappeared?
So, I mean, this PC, I mean, here,
No,
you
it
know,
wasn't
No, it
that
wasn't
slide.
that.
No,
It
no,
was
not
in
that
an
slide.
equation that you had displayed. It was actually,
equation.
yeah, keep going back, maybe.
I don't remember any
Well,
0.42,
no,
but
I think
let,
I
I
think
mean,
you perhaps
I mean,
went
you're
too far.
Look
referring
right
to
there. What's this here?
this one,
This
P
P
max.
min. P min.
Oh, P min. Oh, that's when there's antiferromagnetic order.
That's
Yeah.
what I said.
Yeah. So I didn't show any data on this side. There is a lot of data which I referred to, but everything I talked about was to the right of P min for sure.
Mm-hmm.
These PC1s and PC2s have to do with charge density wave order. They're again
Yes.
nothing to do with them. But you know, so really this PC, this hypothetical PC for FL star to FL, that's never been observed, and that's crucially connected to the fact that once you go into the superconducting state, you know, there's nothing happening at PC. I mean, there could be other stuff at lower doping, but near optimal doping, you know, there's never been a sign of any critical point. You know, there were times when I was hoping they'd see something, but there's never been any clear-cut sign in the superconducting state. And now, you know, more recently we have understood that that's actually very important, and it puts very strong constraints on the structure of the theory. Yeah. So even though this is it's a ghost, if you wish, it's really important to understand what's happening up here. And also, we believe, understand the crossover in the structure of the vortex as you go from here to there. But there's no actual phase transition that people could agree on and exactly where it is. Yeah.
Can I ask a historical question? I know Anderson famously.
Could you stop sharing, Subir, so you can again have.
Yes.
I know Anderson sort of had an allergy to quantum phase T=0 transitions. Was it due to this problem in observing?
It's not for me to speculate what Anderson thought. I mean, I would say that his paper in '87 was absolutely brilliant. It set the right direction and the tone. But almost everything he said about this field since then, in my humble opinion, was not right. So, okay, I'll just leave it at that.
Okay, fine.
Any other questions or comments? If not, let's thank Subir again for a very, very nice talk. Thank you very much. See you next week. Bye-bye.
Thank you.